Hey everyone, today we're going to talk about a pneumotachograph, and I'm not going to talk about the specifics of the device that's attached to a ventilator, but more the concept of how it works. So what it is it's a flow rate sensor, and it senses changes in pressure across the fixed resistance through which gas flow is laminar to calculate flow rate. Now you might be thinking, well, how do we figure out our flow rate based on pressure and resistance? And this is actually quite a common equation that we come across when we talk about fluid dynamics and gas dynamics. And essentially, you can put this into an equation where flow equals pressure difference over resistance. Now, let's take this equation, and if we expand it out further, and we use the symbols such as Q for flow, and our pressure difference is a pressure gradient, so P1 minus P2, over resistance. And we know that resistance equals 8 times length times viscosity over pi times radius to the power of 4. Knowing this, we can then plug our resistance equation into the R on our flow equation. So it ends up being our pressure gradient divided by 8 times length times viscosity over pi times radius to the power of 4. And because it's division by division, it becomes times. So we can then add that pi times radius to the power of 4 to the top part of the equation. And then we're left with this equation that's now complete, which is flow, which is represented by Q, equals our pressure gradient difference, which is P1 minus P2, times our pi times radius to the power of 4 over 8 times length times viscosity. In other words, this equation is also known as the Hagen-Poiseuille equation, which I talk about more in this video linked above. And the important features of this is that it assumes laminar flow, and you need to know the resistance, which in a circuit that's artificial, we can create a fixed resistance. So using this equation, if we want to figure out what Q is, we can create a few fixed parameters that don't really change or are constants that then will allow us to figure out what the flow is. So if we have our circuit here and we put a device in the middle and we know the fixed length of the device, and then within this device we put little tiny tubes and we know the radius of the tubes, so we can then apply pi times radius to the power of 4 to it to figure out that part of the equation. And then next we put little tiny connections on either side of this fixed resistance device, and we put a differential pressure transducer here. We can now measure the pressures on either side of this device, and this will give us P1 and P2. Now the only thing left is viscosity, which is dependent on the type of gas mixture used or the type of fluid that's being measured. But assuming the same viscosity on either side of this green fixed resistance device, then it really shouldn't matter, as it'll be constant between them. So I mentioned before that a pneumotachograph, it makes the assumption that we're measuring laminar flow. So a part of the reason why this small device in the green has these small little tiny tubes is because they will help to create laminar flow, or the assumption of laminar flow through them. So we have our air coming through and it's all turbulent, and then when it hits the green sort of mesh or fixed resistance device, the tiny little holes and pores will let the air flow through them in hopefully a laminar manner. And then, as you can see here, that if you've got air that's coming in and it's turbulent and it hits this fixed resistance device, the pressure will build up, and this will be measured through our differential pressure transducer. Air will then be pushed through the little cylinders, and then the pressure on the other side will drop as the air is slowed and tries to push through. You can see here that there is an error that can occur as we're making the assumption that flow through these tiny little tubules is laminar. So unfortunately, when there's decreased laminar flow, there's also decreased accuracy of the pneumotachograph. And laminar flow is largely determined by Reynolds number, with a number less than 2000 meaning increased likelihood of increased laminar flow. The equation for Reynolds number, for completeness, is the inertial forces divided by viscous forces, which is flow rate times vessel diameter times gas density over gas viscosity. And you can see here that a part of this is gas viscosity, which is a part of our equation for flow, and viscosity is dependent on the gas mixture and temperature. So the gas mixture we have control over, and we can calibrate the circuit just based on the gas we use. But then to manage temperature, we can use a heating unit that's put into this device to maintain a constant temperature. And this decreases water condensation and maintains a constant viscosity of gas going through it because the temperature is kept the same. So these are more factors that we can control for. Now, because we've got this specific device that measures P1, P2, we have our cylinders that have a known radius that help to maintain laminar flow. We know the length of that part as well, and you can apply that length between the P1, P2 as well. And we can calibrate the circuit to gas viscosity. We have all the elements of this equation to now figure out our flow. So now when we think about flow, flow isn't just a volume. Flow is a volume over time, so liters per second. Now, what's really cool about the pneumotachograph is that if you know how many seconds, or you calculate how long you're measuring for between P1, P2 and all these other variables, you can then figure out the volume that is delivered to the patient and returned back to the ventilator. Because all you're doing is timing the time that you're measuring the pressure changes on either side. And then because you measure that time, you then know exactly what volume. For example, if your flow is 1 liter a second, for example, then you would expect that if you measure it for 3 seconds, you would have 3 liters of volume. And what's really cool about this system is that not only does it measure the direction of flow from ventilator to patient, but now you can also measure what comes from patient to ventilator. And this is really important because it can help you understand or help you identify things such as breath stacking or how much is actually being delivered to the patient. And you know, for example, that if you deliver 500 ml of volume to the patient and they only breathe out 250 ml, then they must be breath stacking or retaining about 250 ml, or there's a leak in the circuit where that 250 ml is going. So this diagram doesn't really represent a pneumotachograph in real life. It's purely here to try and explain the concept of a pneumotachograph. There's lots of different types of pneumatochagraphs, but this video is just purely an explanation of just the concepts behind how it works and how it's actually figuring out the flow. If you want to see more physiology videos, feel free to subscribe and leave comments on what you want me to cover, and I'll cover it in the next videos.